There was one other thing I did, and it's actually part of what I'm interested in doing more generally. If you look at the class schedule, I have separated out the C2S11 from the C2S13. So C2S11 actually has sections 11 and 12. For the most part, we've skipped 11. I will be referring to exceptions off and on in a few cases in 11. But now, at this point, C2S13 is, I just sort of cut it out and made a different section. I'm trying to make the sections shorter. Ultimately, I'd like to go so that each section or each piece is a fairly small segment, and do more pieces so that the videos are shorter for each piece. So that when you're listening and looking for something, you don't have to go through 75 minutes to find something at minute 42. If the videos are only 10 or 15 minutes, then it's much easier to find something in particular talk. So that's sort of what I'm moving towards. At any rate, so these I've sort of moved chapter 3 S1 down. So what I'm hoping to do is to finish section 13 and 14, and that's what I plan to do today. And then we're going to go into 3, which is an object-oriented programming. So going into section 13, I was looking for this phrase last time. Let me first of all do a couple things. I'm going to put the works. I want to make sure I set the working directory to be chapter 2, and then I'm going to look at the workspace, and I'm going to clear it just so we're starting out with a clearer workspace. And at this point, I'll look at it this way. Let me go ahead and knit this so that we can refer to this off and on. Last time, I was trying to find this second paragraph, because that paragraph is one of the most important paragraphs that I have written. First of all, the first paragraph sets the stage for the second paragraph. A symbol is said to be bound to a function, if a symbol is bound to a function argument. And so if you have a function argument, you have a symbol, and when you call that, you call it with some value, and that value gets bound to the symbol within that function. So if a symbol is bound to a function argument, it is said to be a bound symbol or a variable. Again, I'm using the word variable and symbol somewhat interchangeably. But if it's not bound, but it's defined in the function, it's said to be a free variable or symbol. So you have the concept of a free variable, which is not an argument, but it's in the function. So then the question is how do you get the bindings for the three variables? That's the key thing. If I have a function and I call the function with certain argument values, they get bound to the actual argument names or symbols. So we know that. So it's easy for the bound variables they're defined automatically. But what is not automatic is how do you bind the values to the free variables within a function. And so here's the sentence. If a free variable is looked up in the environment in which the function is called, then the scoping is said to be dynamic. So if I look it up in the environment in which the function is called. So if I call a function from the global environment, like at the terminal, then it looks it up in the global environment. On the other hand, if a free variable is looked up in the environment in which the function is defined or created, then it is said to be static or lexical. So that's the key. Do you look it up where the function was created, or do you look it up where it was called from? So that's sort of the key concept you have to keep in mind. Now, as I mentioned to you, or I like Lisp, is a lexical, it has lexical scoping. And sometimes we say it's static. Because once you define it within an environment, it freezes it. Now, if you think about it, if you have a graphical interface, you have this event loop. And you can think of this event loop sort of like in R as the global environment. So if I click a mouse, that mouse click can automatically affect certain functions or calls or methods. And so it's convenient for a graphical interface to have a dynamic language. On the other hand, if you're defining things statistically, we often want it to be lexical. So ideally, you actually want a blended language that has the capabilities of dynamic in certain cases, but static in other cases. Now, certain languages like C++ and Java don't give you that flexibility. Others, like Objective-C, do. So I gave an example here. I'm not going to completely go through everything we did in this section last time. And then I define a function. Now, I want you to look at that. Y, if you look at the workspace in the lower left, y equals 10 is defined in the global environment, right? I'm sorry, y equals 20 is defined in the global environment. Y equals 10 is defined within what will be the closure for the function foo. And then I have there's what's called an anonymous function. An anonymous function is a function that doesn't have a name. So I have a function inside foo that's just denoted by function of x plus y. It has no name. So we could call it an anonymous function because it doesn't have a name. So we'll name it anonymous. That is what's returned from foo. In other words, foo returns a function. It returns an anonymous function. So therefore, if I do something like this, if I say bar equals foo, and by the way, foo has no arguments. So I just say bar equals foo with no arguments. So what is bar? Bar is a function. It's the return. In other words, foo returns a function which gets assigned to bar in the global space. In other words, bar is a function in the global space, just like foo. However, when I did this, I formed what was called a function closure. That is, I have a closure around foo relative to this function called x plus y. X plus y was defined in the environment created by foo. So x plus y was created in foo's environment, not the global environment. Well, I guess I'll click through that. It is a function. So if I say bar of 3, it's 13, not 23. Because the function, when I say bar of 3, remember bar is this function x plus y. Bar is the function. It's not foo. It's the result. When I define bar, it's not foo. Foo gets evaluated and returns x plus y, the function. So bar is actually a function x plus y. So when I say bar of 3, and remember that function is defined with x as an argument. So 3 gets bound to x. Where's y defined? Well, under dynamic scoping, it would be 23. It would find it in the global environment because I called it from the global environment. So if I call bar from the global environment, it looks in the global environment to find the value of y. That's dynamic scoping. The lexical scoping doesn't do that. It looks in the environment in which the function was defined. Where was it defined? It was defined within foo. And there's a local variable called y within foo. That function closure includes the function as well as that local variable y, which is 10. Now this may seem subtle to you, but this becomes extremely important a little bit later on. We're going to do maximum likelihood estimation a little bit. And in maximum likelihood estimation, you have data. You have some, let's say you have some density function, and it depends on a parameter, let's say, as well as data. So we can think of it in a couple ways. We usually think of a density function as a random variable that depends on some parameter. We can flip it around and we can think of it as a parameter conditioned upon the data. And then if we ask, what is the value of the parameter that maximizes this function relative to the data? That's what we call a maximum likelihood estimator. So when I'm doing function optimization, when I'm trying to find a maximum, I've got this data hanging around because I'm finding the max relative to the data. Now, if I had dynamic scoping, I would have to define the data. If I call it from the global space, which you would do if you were doing it from the command line, if I call it from the global space, I would have to define all that data in the global space. And then if I had another set, I would have to define it, another data set, I'd have to define it in the global space. Typically, you don't want to define things in the global space. You want to encapsulate them within something smaller, more contained. So it turns out that you can actually capture the data within a function, within a likelihood function, and so you form a closure so that you are working within that space where you define the data. And so I'll get to that in a minute. And that's not something that would be much more difficult to do, much more difficult to do in a dynamic language. So again, dynamic languages and lexical languages have, or static languages have, pluses and minuses depending on what you're doing. If you're doing a graphical user interface, a dynamic language is really, really nice. But it's maybe not so nice for doing statistical computations. So there are pluses and minuses. So if you have a graphical interface and you want it to be highly responsive, then a dynamic language is great. Well, there's another definition here. Functions such as foo that have an enclosing environment are referred to as closures. There's actually two different languages that are at play on the word closure, C-O-O-S-U-R-E. One of them is Clojure, C-O-O-J-U-R-E, which is a Lisp language that runs on top of the Java virtual machine. So I've talked about Lisp here, and a Lisp is the language historically and currently, to a large degree, of artificial intelligence. It developed in the artificial intelligence community. It's used very widely for a variety of reasons. But if you wanted to be more flexible in how you use Lisp, it turns out that you can actually run Lisp on top of a Java virtual machine. So for example, on an Android phone, you actually are running on a virtual machine, a Java virtual machine. It's called a VM. There's another closure called COOZURE, which again is a Lisp language. It's not running on the virtual machine. And then Google has actually a type of language relating to JavaScript that's built on the concept of closure. So the idea of a closure, in essence, I form a foo. When foo gets defined, it forms an encapsulated environment with these local variables, and it has a function in it. And those functions, they'll self-contain in essence because the functions can get their free variables from that enclosing environment. Now, there are also rules that if it doesn't find there, it can sort of, if you think of aura, you have environments and you've got environments within an environment within an environment. And so there are also rules that let you, if you don't find it in the inner enclosure, you can go out one level and out one level and so forth until you find it. And so R gives you quite a bit of flexibility on where you find these values. Okay, I covered this last time. I didn't want to recover everything. I wanted to go down to likelihood. So we're going to take a simple density function, the exponential density. It's very common. Not as common as the normal, but common. It's used a lot in a lot of areas. For example, in reliability engineering, it's used quite heavily. So we have the density f of x is equal to mu e to the minus mu x. And we're assuming that x is greater than 0 and mu, which is the mean, is also greater than 0. And a lot of times we will specify the mean in terms of a rate parameter called lambda, so it's 1 over lambda. This actually becomes important in terms, a little bit later, this becomes important. I need to define that a little better because lambda kind of came out of the blue. So we often see that defined. We often see that as 1 over lambda e to the minus x over lambda instead of seeing it in the way it's written here. This is a slightly different parameterization that you usually see it in. And again, it's just a different reparameterization. If I use mu or 1 over, if mu equals 1 over lambda, it doesn't really matter, except how you interpret the parameters. Okay. Now, if I get a random sample, x1, x2 up to xn, if I have a random sample and I want the joint density of all the x's, so let's say I have a random variable x1 and I have a random variable x2 up through xn, and they're independent. So if I get a random sample, they should be independent, right? So if I get a random sample, they're independent. So if I want the joint distribution, then how do I get the joint distribution? It's the product of the densities. And the reason I can do a product is because of independence. It's sort of like saying the probability of A and B is equal to the probability of A times the probability of B. I'm taking a product. And why can I do that? Because I have independence. If I have independence between the events A and B, then I can say the probability A and B is equal to the product of the probability of A times the probability of B. That's sort of the same idea here. It's sort of not my intention to be teaching maximum likelihood estimation in depth. You can look at any stat book for this. But I can think of it as the product of the f sub i's. In other words, x sub I, I get a product, and then I take the log of it. If I take the log of that product, it's n times the log of mu minus mu times the sum of the x sub I. So what I've done is I've taken the product. Maybe I'll write a few more lines here to fill it in. But if I take the product of the f sub I with respect to x, so x1, x2, there's a subscript on the x's in that first equation, in other words. So I take the product, and then I take the log of the product, then I'm going to get n log of mu minus mu times the sum of the x sub i's. So that's what's called the log likelihood. And so I want to maximize that with respect to mu. I want to maximize the log likelihood. That's the problem we want. So we could plot that if you knew the x's, like if you collect the data and you know that you can, if you know the x's, I can compute the sum, right? And I know n, that's my sample size. So if I know n and I know the sum of the x of i's, then I have a simple function of mu now, and I can find its maximum. I can find the value of mu that maximizes that. So I could define an R maximum likelihood function. I'll call it RML function. And what I'm going to do is I'm going to say that the sum of x is equal to the real sum of x, where x is a vector of the data, and then n is the length of x, which is the sample size. So I have a vector x, and that's my data. I have a vector x as my data. However I get the vector, I collect the data, that's my data. So I can sum it, and I can take the length of it. That gives me the sum of the x of i's, and that gives me n. And then I define a function. Notice how I define the log likelihood function. The argument is mu. And so, if you look here, and then you look at the R code, it's like there's a one-to-one correspondence. That's really nice that we can just write the R code that mimics the algebraic code, or the algebra. So I have n times log of mu minus mu times sum x, where sum of x, again, this argument is going to be called of x, right? So sum x in that function, the likelihood function, that's a free variable, right? But it's not the only free variable. Both n and sum x are free variables. They're not the argument to the function RML fun, right? They're defined locally within that function. You sort of see what's happening here? So I define two local variables within the function. And then I define the log likelihood function. And that's defined in terms of two local variables that are not function arguments. The function argument for that local variable, that local function, is in fact mu. Well, if I need to maximize that, and I need those two local variables here, suppose you had a dynamic language, it actually wouldn't find them. So it would look if you called it from the global environment, it would look for those two in the global environment, not the local environment. That would mean you'd have to define the sums and the n's in this global environment, and it's not nicely encapsulated. So here we can nicely encapsulate it within this maximum likelihood function, R function. So this is kind of nice. Okay, let's go back here and take a look at that a little bit. So I'm going to go back. By the way, I found out the problem we're having is periodically we have someone processing huge files. And during the last class when we went down, that person was using 95% of the resources of our system. And so, of course, it cut us out. So I need to figure out, I may have to separate the teaching machine from the research machine so that people don't do that on the teaching machine. Or if they do, they automatically get killed. We actually killed it last time, and that's why some of you got on later in the session, because we killed the session. So if you're running this huge job, please don't do it during the day. Okay, let's define this function. So I just defined the function, and then I could say e function. The data I'm gonna give it is the vector 1 to 10. Okay, 1, 2, 3. That's the data. I'm just being lazy here, or the book is lazy. So what I'm gonna do is I'm gonna assign the e fun. Now notice that e fun is in the global space, right? And it actually, what is e? What does e? What is it? E fun is the log likelihood function. So in other words, it returned this last thing. The return from the function is the log likelihood function. That's what gets returned, and that gets assigned to efun. Okay, and so in principle, then we could actually get the maximum likelihood. But I'm going to come back to that in a little bit. Now. I can define another function, efun2, which has another set of data. So that's another set of data. This goes 20, 21, 22, up to 30. So that's another set of data. It's not really data, but pretend like it is. It has values 20 to 30. And so if I do efun of 2, that actually evaluates. What did this do? Oh, I'm sorry. Up above, I should have evaluated this. Up above, and it doesn't matter because efun, this actually evaluates the likelihood function at mu equals 3. We're not finding the maximum here. This just evaluates the log likelihood function at mu equals 3. And that's what it does. So it's for the first case, for efun, it's a minus, which is the data 1 to 10, it's a minus 1 to 54.01. And for efun2, which has another data set, it's minus 812. So, well, I won't do that again. The point is, I could just sort of experiment around and sort of, suppose you were trying to find the maximum, you could say, okay, let's take efun. So for efun, I could type in efun 5, okay? I could type in efun 1. So if I'm trying to find the maximum of this, I need to do a little bit more. In other words, I can find individual values of the log likelihood function, but I need to find what the maximum is, right? So I have to do a little bit more. So we could talk about function optimization. And one of the commonly used methods is Newton's method for function optimization. Now, in this case, the likelihood function you can show, or if the likelihood function is convex in the parameters, and you can show that in fact is the case for the exponential, that it is convex in U. So if it's convex in the parameter, then what you can do is set the derivative of that function equal to 0, and when you solve for that 0 value, that's, in fact, what will maximize it. That's basic calculus. So we set the derivative, we set the derivative equal to 0, and we actually solve that problem. Now the derivative of a log likelihood function is called the score. It's called the score statistic in particular. And so what we're doing is setting the core statistic to 0. And in order to do that, see, that's the function f. The function f is the one we're setting to 0. So that's like the first derivative already. And then the function f prime is like the second derivative. And so we have, so the function f is not the density f, it's the derivative of that, actually the derivative of the log likelihood. And the function here, f prime, is actually the derivative of the second derivative. So I need the first and second order derivatives in order to use Newton's method to solve the maximum likelihood problem. So let's take a look a little bit more. So if in addition, and again, if you know calculus, you can follow this. If you don't, you'll have a little more trouble. Suppose we define another function that the first 3 lines are exactly the same as what we defined before. So those first 3 lines, n sum x and l Those are the same. But now I define a score. Now the score is going to be the first derivative. So if I take the derivative with respect to mu of n log of mu, what is it? The derivative of n log of mu with respect to mu. It'll be n over mu. That's the first derivative. And then I have minus mu times the sum of x. The sum of x is constant. So the derivative of something linear, it just disappears, right? So you just end up with minus something. So the first derivative, if I take L fung and take the first derivative, I get n over mu minus the sum of x's. Then if I take the second derivative of that, I get minus n over mu squared. If I take the next derivative. Okay, so I have the L fung, which is the log likelihood, and then the score, which is the first derivative with respect to mu, is the next line, and then the second derivative with respect to mu is the next line. So I need what I actually need are those last two lines to use. I need the score and the D2 in order to use Newton's method. That's what I need. Because I'm setting the score equal to 0. And then I can solve that in terms of that derivative of the score function. So let's so that's the L fun. And then if we define Newton's method, we can look at Newton's method, and we'll sort of see how this goes. So let me go back to the R code. You need to look at this carefully. So we're defining this general function. And again, it has a log likelihood, it has a score, the first derivative of that, and the second derivative of that. And this function actually returns all three. Now, what does Newton's method do? Oh, let's see. I want to come back to this a minute. I don't want to use that form. That's in the book, but I don't want to use that form. Let's see how I did this. Yeah. Okay. I'm going to define a slightly different form called L fun. I'm going to define a function called L form, which has n the sum x, it has a score in D2, and it only returns the score in D2. So L fun is going to just give you the n, the sum x, the score, which is a function of mu, and D2, which is also a function of mu. Okay? Now, if I wouldn't put that last list, in other words, the last list returns what? It returns a list with both functions in the list. If I wouldn't have put that list and just left that line out, what would have gotten returned? D2. Only D2. But I actually need D1. I actually need both the score and D2. I need both of them. So this is a paradigm we often use in R. A function will return its last statement. So if I didn't have that line of list, it would have returned D2. It would have returned a function it would have returned D2, the function D2. But I actually need score. If you look at Newton's algorithm, it needs f and the derivative of f. It needs both. So I need the score and the derivative. Right? So I'm going to return both. So it says list, score equals score, D2 equals D2. It's going to return two named objects. The first name will be score, and it will contain the function. Okay, it will contain the function. So if I, for example, said temp I'll just put some arbitrary data in here. And then if I look at temp, see temp is a list that has two elements. $score, that's the first element. It's the score function. $D2, it's the second derivative. It's the second element. So when I return, I'm returning both the score function and D2. Now let's look at Newton's algorithm. How do we program it in R? We'll execute it. I'm going to give it as the first argument a likelihood function. The second argument is going to be a guess. You have to tell it, you have to give it some initial value. And in order to give an initial value, you have to kind of know where it might be. You can't be way far off. In some cases, it may not converge at all if you're too far off. And then I give a tolerance. A tolerance, you're going to have potentially, we're going to potentially have an infinite loop if we're not careful. So we're going to do two things. We have a tolerance. If we get close enough, we stop. But we also have a maximum number of iterations. If you didn't have a tolerance and you didn't have a maximum number, and you say, well, this is true, and if it never converges, the program would run forever until someone killed it, which might be Steve. If you happen to run something that runs forever, we will kill it at some point. So those are the arguments. The likelihood function is the first argument, which we've just defined, right? The second argument is S, the estimate. That is my initial guess of what it might be. The tolerance, that's a stopping rule, as well as the maximum number of iterations, which is a stopping rule. So I say C-score. What C-score says, I pass it a likelihood function, which has two components. So I say L-fun $score, and that score has an estimate, right? It's my initial mu. So C-score is what? It's the value. It's the value of the score function based on my initial guess. Now the score function, I'm trying to find a value of mu that sets it to 0. So I say, if the absolute value of the score function is less than tolerance, if it's near 0, notice the tolerance is very small, right? So if it's near 0, I'm finished. I return the parameter estimate. If I'm not close enough to 0, I'm trying to find the derivative of the likelihood function that's equal to 0, which is the score equals 0. So I'm trying to find the value where the function passes through 0. I'm trying to find a value of x that gives me a 0 for the function, the likelihood function, the score function. So, but if that's not the case, then I go into an iteration, and this next line, nu equals est minus the score function over the second derivative function. Go back and look at the definition. That right there is precisely that function right there. My initial value minus the score function over the second derivative function is equal to my new value. I encapsulated that. But this f right here is actually the score function, and the f prime is actually the d2 or the. Okay. So that code exactly is that. Takes my current estimate, subtracts off the score over the d2, and with d2 I get the value at est, and then I get a new value. Okay. And then I evaluate the score function again at this new value, and I say if this value is less than the tolerance, then I return the new. If it is not, I set my try at the new value. I set est at new, and I go back and I iterate again. And I iterate again by default 500 times. If it never converges to within that tolerance, I break out of that loop, that for loop, and I say stop, exceeded the allowed number of iterations and never converged within 500, is what that means. Now you can change the 500 to 1,000. But this is Newton's method. Do you see how it works? So I could pass I could create a likelihood function. I created the likelihood function right above it, right? I created that for the exponential, but I could have done it for the gamma. I could have done it for any distribution you give me. Well, some of them are not well posed. That is, some of them are not convex. So if I don't have a convex function, this breaks down. So now I'm simply going to, let's see. I'm going to define a likelihood function based on the data of 1 to 10. You could put any data in. You could have a real data set. That's what you put in the argument. It's going to define a likelihood function with a closure. What's that closure going to contain? It's going to contain the sum of the x's. It's going to contain. Now, granted, if I have another density function, I have to redefine that likelihood function for the new density function. For the exponential, I need the sum of the x's. I need n. And then I define two other things: the score function and the second derivative function, d2. Okay, that forms a closure. So the score function and d2, when they need, if they need the sum of the x's and n, they find it within that function closure. You may get used to it if you read it enough and think about it enough. This is not trivial, I agree. Particularly if you haven't had a programming language. And if you have, even if you had, maybe you have C and you saw it one way, the way C does it. Okay, so I'm going to define this. Now, L1 func, well, let's see what it is. It's a function closure, right? But it has these two components to it. That's the requirement I need for that function Newton. I needed a score and I needed a D2. Look at the code. It's got, right here, it's got L-fun score, and the argument is going to be some value of mu, whatever my current value it is, and D2. Here's D2. So I need those, and so I should have them. So I'm going to call Newton with this function closure that I just created as my first argument, and my guess as the second. Now here's where the killer comes in. Now if I take 1 to 10, can anyone tell me what the mean is? What's the mean of? If I take 1 plus 2 plus, what's the mean? 5.5. Okay. So if you just want to think about the general rule, if I sum 1 to n, what in fact is the mean? So it's n plus 1 over 2, yeah. So it turns out that that mean is not the mean of our exponential. It's 1 over the mean. That says that 1 over lambda. So if I take 1 over roughly 5, I get about 0.2. So I know 0.2 is going to be close. And so I use 0.2 as my initial guess. I mean, actually, I know, I actually know the answer here, so I could have used exactly. So I'm going to, my initial guess, and if you don't know the initial guess, I'll show you what you can do. And so that's the exact estimate. That's the maximum likelihood estimate is 0.18. Now the point is, this method we developed, the Newton method is general. As long as I pass it a convex likelihood function that's self-enclosed in terms of the data that you need in order to evaluate the score in the second derivative function, this works for any. Any distribution. If you wanted the gamma distribution, you could do this with a gamma. Now, you need to be able to take the first and second derivatives, which you happen to be able to do nicely with the exponential. That's one of the reasons you pick the exponential, because it's easy to get the first and second derivatives. If you can't get the first and second derivative in closed form, then those get iterated. And or I actually can do this. Or I can numerically approximate first and second derivatives. So if you had like a normal distribution, which is not so easy to get first and second derivatives of, then you need slightly more sophisticated, you need slightly more sophisticated methods. Okay? Okay, so I want to here I was just showing you that we define a function closure here, but there's another way we can do it. We could define an environment, and then I say, okay, E1 is a new environment, and E of A is in that environment. If I define foo, then what I can do is I can define that foo within the environment E1 by using the argument, using the function environment. So environment of foo is E1, so that sets the environment. And then you get what you would expect. And if I change the value of A within that environment and re-execute it, then this works. So that's another way you can do it. You can explicitly define an environment, and you can populate it with local variables, and then you can actually force that function to be in the environment using the environment function. So that's another way. The way that I did it previously using the exponential and likelihood is the more normal way of doing things. Well, let's suppose that you didn't exactly see if this is going to work. Yeah, this has been happening to me today, so we'll look over here. These arguments, there are certain arguments that I'm having trouble with the margins, but it works if you run it in RStudio. What I was doing was that is the likelihood function. That's a graph of it. Now, do you notice where it's maximum? First of all, I'm plotting the x-axis. Now, the maximum is about 0.18. We figured that out, right? We know where the maximum is, about 0.18. And so I'm running the x, just to show you this function, I'm going from 0.1 to 0.3 in increments of 0.01. So I'm going 0.1, 0.11, 0.12, and I get a fairly smooth curve if I do that. And then e-fun I'm calling at the same, I'm calling that e-fun with the same x. So I'm actually evaluating the likelihood function. What I'm doing is evaluating the likelihood for a whole bunch of values. So this, if you define a likelihood function and you needed an initial guess, you actually could do a graph like that, and you say, well, it's about 0.2. But in fact, we figured it out. It's exactly 0.18 something. So if you don't have a clue as to what the initial value is, in R it's quite easy to plot the likelihood function, or any function you're trying to optimize on. So here we could have plotted it and said, oh, okay, I need an initial value. And you can kind of guess about what it is. And then the algorithm finds it very quickly. Now, if I would have picked 0.3, it's going to take a little longer to converge. But you can see that's a convex function, so it's very nicely defined. Okay. Well, I kind of want to stop here. If I define here's the Poisson distribution. Depends on lambda, which is, for the Poisson distribution, both the mean and the variance are lambda. So it's e to the minus lambda, lambda to the y over y factorial. And notice that the Poisson the Poisson of y given lambda as a parameter can be defined in terms of y minus 1 given the parameter times lambda over y. So if I multiply Poisson at y, if you look at Poisson of y, it can be defined at y minus 1 times lambda over y. So in other words, that's defined recursively. I've defined the Poisson in terms of itself, right? That's a recursive function. The other day when we looked at it, we had a doubly recursive function, which turned out to compute n factorial in a very obscure way. This allows you to recursively, so I just want you to look at the code for a minute. Maybe it's easier to look at the code here. So here's the recursive Poisson. It's a function of y and lambda. It says if y equals 0, you return the exponential of minus lambda. Else return the recursive Poisson, it's calling itself, at y minus 1 of lambda plus lambda over y. So if y is 5, then it's not 0, so it calls it for, to evaluate 5, it calls it at 4 multiplied by lambda over 5. And then it recurses around again and calls it at 3, calls it at 2, calls it at 1. And finally it evaluates here, but then it starts going back up. So it's sort of cycling down, and it finally gets down to 0, in which case it knows the value. And once it knows 0, it then can find the value at 1. Then once it finds it at 1 and 0, it can find it at 2, and so forth. And then it cycles back up to give you the value. So you might want to think about the logic of that. We can actually, this is a Poisson. I want the probability y equals 4, given that lambda equals 3. And let's see how this works. And that gives the probability. Okay. Now, there's a built-in function called dpoise. That's a built-in R function. I'm going to round off here. So this here I'm going to get the probabilities from 0 to 13. This, by the way, the function that I wrote there is not vectorized. But this dpoise, which is the density at the various values of y, for lambda equals 4 in this case. Lambda equals 3. I'm rounding off to 4. So this is the built-in function. This is lambda equals 3. I'm evaluating it at 0 through 13. So I'm going to run this, and you can see the value, the 0.16 right here, and this is y equals 4. In other words, I start at 0, 0, 1, 2, 3, 4. So that value that's shaded is, in fact, what I just computed recursively. So dpoise is a built-in R function. The only reason I showed you the recursive one is just to show you can do it. Okay. So that actually ends this section and ends the chapter. Other than the fact that, yeah, I might mention a couple more things about graphics. Read the last section. It talks about devices and things a little bit, so you might want to read that. But we're going to start on chapter 3 next time. Okay. Any questions? I would recommend that you look at